In this video, we'll talk about the surface area of the graph of a function. So in the special case where we have a surface with the equation z equals to f of x comma y, it can be parameterized by the equations x equals to x, y equals to y, and z equals to f of x comma y. And therefore, the vector function of the surface is equal to x times the vector I plus y times the vector j plus f of x comma y times the vector k. And if we take the partial derivatives of the vector function with respect to x, we'll have partial derivative with respect to x of x, which gives us 1 times the vector I, plus partial derivative of y with respect to x, which will give us a 0 times the vector j, plus the partial derivative of f with respect to x times the vector k. And for the vector ry, we have partial derivative with respect to y of x, which will give us a 0 times the vector I, plus partial derivative of y with respect to y, which gives us 1 times the vector j, plus the fy times the vector k. And therefore, the cross product between the vectors rx and ry will be equal to the third order determinant with ijk 1, 0, partial f partial x, and 0, 1, partial f partial y. And if we evaluate that third order determinant, we have that it is equal to the negative partial f partial x times the vector I minus partial f partial y times the vector j plus the vector k. And since the magnitude of the cross product between the vectors rx and ry is equal to the square root of 1 to the square, so we have here 1 to the square plus partial f partial x to the square, or since f equals to z, you have partial z partial x to the square plus partial z partial y to the square. Then the area of the surfaces is equal to the double integral over the region D of the magnitude of the cross product between the vectors rx and ry times dA. And this is equal to the double integral over the region D of the square root of 1 plus partial z partial x to the square plus partial z partial y to the square times dA. Let us see an example about that. We're asked to find the area of the part of the paraboloid x equals to y to the square plus z to the square that lies inside the cylinder y to the square plus z to the square equals to 4. So for the paraboloid parametric representation of that surface is that x equals to a function of y and z, which is equal to y to the square plus z to the square, and y equals to y, and z equals to z. And since that we have the part of the paraboloid that lies inside the cylinder y squared plus z squared equals to 4, we'll have that 0 is less or equal to y to the square plus z to the square less or equal to 4. And this defines the region of integration D, let's call that. So that defines the region of integration So now we have the region of integration D in the polar coordinates in the YZ plane. So we have in the YZ plane, the region D in polar coordinates will be given by the set of points with r theta, such that we see from here that r takes values between 0 and 2, with 0 and 2 included. And also there's no restriction for theta, so we have that 0 is less or equal to theta less or equal to 2 pi. So one thing that we should note here is that if the surface is described by x equals to a function of y comma z, then the cross product, we'll need to take the cross product between the vectors ry and rz. And if we evaluate that, this is equal to the vector I minus the partial derivative of f with respect to y times the vector j minus the partial derivative of f with respect to z times the vector k. And therefore, the area of the surface S will be given by the double integral over the region D of the square root of 1 plus partial f partial y to the square plus partial f partial z to the square times dA. So this is equal to the double integral over the region D of the square root of 1 plus, so for the partial f partial y, we have that it is equal to 2y and all to the square. So essentially, we have the partial derivative of f with respect to y, which will give us a 2y for y to the square. And then we have the partial f partial z will give us a 2z, and that to the square times dA. So the 2y on all to the square plus 2z and all to the square will give us a in total of 4 times y to the square plus z to the square. And y to the square plus z to the square is equal in polar coordinates to r to the square, so we'll have 4r to the square. So if we convert to polar coordinates, we have the integral from 0 up to 2 pi for theta, and the integral from 0 up to 2 for r of the square root of 1 plus 4r to the square times dA, which is equal to r dr d theta. And if we split now the two integrals with respect to r and theta and multiply, we have the integral from 0 up to 2 pi d theta times the integral from 0 up to 2 of the square root of 1 plus 4r to the square times r dr. So that is equal, integral of d theta will give us a theta, which needs to be evaluated between 0 and 2 pi. And for the integral of the square root of 1 plus 4r to the square times r, we need a u substitution. So setting u to be equal to 1 plus 4r to the square, we'll get that 1/8 du is equal to r dr. And therefore we have times the integral of 1/8 u to the 1/2 times du. So that is equal to 2 pi for theta. And then we have 1/8, which we can pull outside the integral. And we have the integral of u to the 1/2 will give us a 2/3 u to the 3/2. U to the 3/2 is equal to 1 plus 4r to the square and all to the 3/2, evaluated between 0 and 2. And if we evaluate that, this is equal to 2 pi. From the 1/8 times 2/3, we get 1/12. And then we have, for r equals to 2, we have 17 to the 3/2. And for r equals to 0, we have -1. And if we simplify here, we get that this is equal to pi over 6 times 17 to the 3/2 minus 1.